So this is just a friendly introduction to graded rings. So one of the topics that I think some people here are also interested is that, and we talked about this yesterday, is if you have a graph, then you can associate an algebra. This is an algebra to this graph. And the first thing you wonder is that you change this graph, you get different algebras. What are these algebras? And it's a ring, which is a vector space, so it's an algebra. How do you study these? How do you study these algebras? You'll see maybe in next session that these are Z-graded. So these are Z-graded rings. In fact, you can put any grading on them. So, and this grading behaves very well in this setting, okay? For that reason, I'm gonna just cover the basics of graded ring theory, and hopefully, if we know that technique, we can apply it here, okay? So, what we are gonna do is the basics of graded ring theory. And, well, the basic idea is that if you have an object, so imagine you have a mathematical object S, well, you can study this, right? You look at this globally and study this. But sometimes you are able to partition this. Okay, so I partition this, if I can. And the way I partition this, maybe I have to index them by something. Because I'm doing algebra, I'm going to index these maybe by a group. So these alphas are coming from a group. So I partition these, and hopefully I would be able to look at these partitions and study these partitions. And the whole idea is that first I partition, and then I would be allowed to move the partitions around, to rearrange them. That gives you a lot of power, okay? So you'll see again in this setting, not only I can partition, then I move the partitions, and that gives me a lot of information about the algebra. Okay, so let me start with one type of this partitioning on a ring. So let me just remind you what we have. So imagine definition. R is a ring. And I just remind you what this means. That means that R is a set, is a non-empty set, and it comes with two operations. One of them is just you can add the elements, and with that you have a abelian group. Okay, so you can add, you can subtract, that gives you an abelian group. And the other one, a totally different operation. Here you can just multiply. And you have an identity, okay? So it's a semi-group. That's just a name for it. You can multiply with identity. Okay, so two very separate operations, both on this R. So, well, you have this. Now, in order to define ring, I have to interrelate these two. Right? At the moment, these are two separate operations. I have to connect them, and this is the connection. I mean, the most natural thing you need to do. So you have an A from here, B plus C. So B plus C is happening with this addition, A times is happening here, and I want to connect these two. So, and I'm sure you can guess what I want to write, and then, as always, you swap the positions, you want that to also. This is called distribution. Okay, so that gives you a ring. So I have two operations, they are interrelated, that gives you a ring. Then you can do all kind of proof. For example, this has a 0, you can prove that this is the same as this, and this is, you need to prove this, and you can use this one. So use these assumptions to prove this. All right, so examples. I'm sure you know all of these, but let me just warm you up. So this is integers. So you can add, you can multiply, and additional multiplication satisfy this. So this is a ring of integers. And then the next one, immediately, as soon as you have a ring, you look at the matrix algebras. Matrix. And immediately it gets very complicated. All right, so as soon as I have a ring, I have a matrix ring. Just to give you an idea why it gets, indication why this gets complicated. Not why, just indication that it gets complicated. So one of the things you can define as soon as you have a ring, this definition, or a ring, then just get by this notation, all the elements in R such that they are invertible with this operation, with the semi-group operation. Okay, so I collect all the elements which are invertible. Of course, 0 is not. So this is a group. So it, in fact, is a multiplicative group of R. Lots of papers on this. So you start with the ring R. What is this? Already for a field, you can ask. So you have a field, you drop the 0 because everything else is invertible. You drop the 0, you get a group. What is this group? And still very active. Okay, for fields, this is done. But for division rings, so these are fields, but the commutativity is not there. Still, it's not clear what is this group. Now, let's look at these examples here. So what is Z star? What are the invertible elements of Z with multiplication?
1 and minus
1 and minus 1. These are the only ones that have inverses within Z, right? In Q, there are a lot, but within Z, these are the only ones that you can multiply. Now, let's look at the Mn of Z and get the invertible elements. What are these? Let me just introduce a notation, GLN of Z. So this is just in language, general linear group, that these are all invertible elements of this matrix. Now, what are these? And I really like this example. So here you have just 2 elements. Here, this is so big, it contains, well, let me get 2 elements here, 2 very, very simple elements here. This is 1 element here. It has an inverse. One reason is that the determinant is 1. So this has an inverse.
N equals 2.
Yeah, that's right, that's right. Here I put maybe even 2. Correct. Already on this level, this is very, very big. And here is the justification. Look at this one, of course, and then look at its transpose. Right? So first of all, these 2 are in this group, right? Now get the subgroup generated by these. The subgroup generated by this just means all the multiplication of these and it inverses. You just arrange them next to each other. Okay. So let me call this F. So there is a paper in 1947, pretty old, but by a Russian mathematician Sanov, which shows that this is a free group of rank 2. A free group means that, so a free group, if I construct a free group, that means like free algebras, just get 2 symbols and then put them next to each other with any sequence and introduce X inverse and Y inverse also anywhere you see, so you can just symbolically put these next to each other. That would be 1 element of this group. Then if you have another one, just put them next to each other, just concatenate, and anywhere you see X and X inverse, just cancel. So that gives you a free group, which as you can see, it's massive because it's all words, finite words containing x and y, any combination. So it's a very, very big group. And then this paper says that these two, although now they have meanings, but this plays the role of x, that plays the role of y. So this is a free group inside this. So for two elements, this is the largest group you can get. It's already in here. So that shows you, okay, so if you're going for just for a ring to its matrix ring, it gets complicated. All right, so now, in a lot of occasions, if I give you a ring, you can partition. Not always, but oftentimes you can. And then I'm into this business of partitioning, rearranging, and studying each component. So let me just write the definition. Definition. So R is a ring. And here I'm considering that the ring has an identity. You can drop all of these, but for simplicity, let me just assume one is in R, and I get a group. Also, for simplicity, or oftentimes in applications, this is a Abelian group, so I just put a Abelian group. All of this can be generalized. Then, I would say R is called graded, gamma graded ring. If you would be able to slice this R, so now you understand what I'm saying. This R is a direct sum of these R alphas, and these R alphas are subgroups of R. So these are subgroups. So inside R alpha, you can add elements, you can subtract the elements, right? And well, I have R has an addition and multiplication. So what would they do under multiplication? Again, I'm sure you can guess. As usual, you have to go for the most natural way we can think of. So you have an element here. So imagine this is, let me call it of degree alpha. This has degree beta. If you multiply, what would you define to have it the most natural thing? I would say, well, if you have an element of degree alpha and an element of degree beta, you multiply has degree alpha plus beta. So it should come here.
Set multiplication or this multiplication, the sum of the.
Right. Okay. So when I write this, good question. So when I write ij, this is notation for I, the sum of these, yes. Right? But of course, it's enough I say any two elements end up here, then everything ends up there because these are subgroups. So maybe I just put this. So this is my note. When I just write two sets, multiplying two sets, this is what I mean on the setting of rings. Okay. So now, a bit of notations before we go further, and then examples, very natural examples. All right. So first of all, okay, so this is your R, and I partition this here, R alpha, R beta, R gamma, and you understand because I wrote direct sum, they don't intersect. Their intersection is only zero, right? So the only thing sitting between them is zero. And with this definition, when I multiply an element here, I'm ending up in R alpha plus beta. Okay. Then I'm interested in these elements, the elements that you can just write has degree. So this is the notation I use. Homogeneous elements. Did I write this correctly? I think so. Okay. And these are alphas, we say the alpha component of R. And well, if an element is not zero, and this is in R alpha, then I say A is of degree alpha. I still see in a lot of paper, they just say this is of degree alpha, and that's not well defined because zero is in most of all of them. So zero would be, so a lot of people they forget this. So you have to say if A is not zero, then it's uniquely in one of these partitions, then you can say it's of degree alpha. A bit more notations. Alright, so now you can split this, so to say, these pieces, but it's not guaranteed that all of these pieces are actually non-trivial. It is possible some of them are just zero. Okay? So I'm going to pick up those elements from my group such that this component is in fact not zero. So it's genuinely the element sitting here. So I call this the support of the ring R. Okay. So now examples, and I give you a couple of examples from very trivial ones to a bit more complicated one. I think this is, I would imagine this was one of the first example of graded rings, so polynomial rings.
Support will be a semigroup. Support will be a semigroup.
That's right. The support here would be n. Thank you. So now I have to give you, first of all, I have to give you how I'm going to partition these. So can I just put here a field, and this is R. So I'm sure you can guess. And I'm going to say that R is Z-graded ring, so I have to give you all these components. So Rn is Kxn. Can I just write it this way? Kxn if n is larger or equal to 0 and 0 otherwise. Right? So I know the notation makes it heavy, but just all I need is that the Rn pieces is just polynomial of Kxn. And of course, if you have a polynomial of degree n, you multiply with the next one. So Rn, Rm, you are in Rn plus n. And as you mentioned, the support of R, another way to say it here, that might make it a bit ugly, but this would be Z R. That's not a good notation. I'll just put a support of it. Is, well, those components that are not zero, and R0, so what is R0? It just came, right? So R0, R1, and so on, so 0, 1, 2, these are the support, which is inside the actual group set. Now, you have to be careful, the support here has a structure, it's a semi-group, but not necessarily, sometimes it's just a subset. The support doesn't have to be an algebraic structure.
I mean, support must always be a semigroup, right? Because if R alpha and R beta are non-zero, there's some product that is contained inside R alpha plus beta.
No, R alpha plus beta may be a zero.
Oh, yeah.
All right. So we are going to have examples that's going to happen. Okay. So of course, if you have a ring R and gamma group, you can always artificially make this a gamma graded ring. With the most trivial partition. So I put everything in degree 0. If So that makes R a gamma graded ring. So everything is in R0 and everywhere else is 0. So it doesn't give you that much information, but that tells you that the usual ring theory is also included in the theory of graded rings. So if you prove a theorem in the gamma graded setting, as soon as you put, for example, okay, so the other way, no, okay, the other way. So imagine R is a ring, and I get gamma identity. Then R is a gamma graded ring. Can you see this one? So now R is a ring. The abelian group I'm going to pick is this identity. Okay. So that makes R a gamma graded ring. So I have to give you the components. Well, I put R, E, R, and that's it. There is no other things. And of course, this sits into this because R, E, E times E is E, so it sits here. So if R is a ring, that's what I should have said. If R is a ring, now this is also inside the theory of gamma graded ring. That means if you prove a theorem, you say theorem, R is gamma graded, and then you put a statement here. Well, you prove this for any gamma. If you pick identity, that means you prove it for the usual ring also. Sometimes for usual ring, this statement becomes trivial. Sometimes not. Sometimes it covers, the usual ring theory plus everything else. Okay. Now, if you have the gamma graded ring, the first thing is that you want to compare the rings. So, if you're looking at a category, you have the objects. These are the objects. How do you compare them? What are the morphisms? Well, definition. If R and S are gamma graded ring, a gamma graded homomorphism is, well, first of all, these are rings, so phi is a homomorphism. Is a homomorphism of rings such that, can you tell me what I need more? So remember now, this time R comes with all the components.
So on individual components, it must also preserve.
That's exactly right. That's exactly what it should. So I know that phi sends the elements, I know phi sends an element of R to S, but because I'm in this setting of partitioning, I really want to force that D sits here. So I really want this to happen. Or any other. Okay. Now, a couple of the most basic theorem, I just put it here for you. I'm not going to prove it. Proposition. So you have a graded ring. First of all, okay, you have an identity. We said that the ring has identity. This identity always sits in R0. 0 is the identity of a ring, and identity of a ring, identity of a ring sits in R0. 0 is the identity of the group. Okay, so that always happens. Well, you have to write a little proof here for this one, isn't it? Yeah. 2, R0 is a subring. So in itself, now you are dealing with two rings. This is also a ring. Why is that? First of all, one, I just said, is in here, and it's closed under multiplication, right? Because R0 is in R0 plus 0, it's in here. And of course, this is a subgroup already, and the distribution, everything comes down from R, so that makes R0 a subring. So now, once you are in the theory of in this theory, in fact, you are dealing with two rings. One is here, one is here. 3, any other components is a R0, R0 by module. If you remember the module theory, this can be considered as the R0, R0 by module, and this gives you a lot of modules. And this one I'm sure you can guess. Let me see if you can. So imagine you have an element in R alpha and it's invertible. Remember we were talking about the invertible elements, multiplicative subgroup of a ring. So if you have an element which is invertible, so can I just put it here, this name X is invertible. Where is the inverse, you think? Where does the inverse sit? That's right. I can put it here also, but I don't. So if X is invertible and it has of degree alpha, its inverse is the opposite. Okay. And you see a lot of paper already, because this is not a very young subject in this setting, is that, okay, you have this ring R, then you have this R0. One of them is that how much this R0 influenced the whole structure of R, right? So you see a lot of theorems of this form. If R0 has property P, then R has property Q. So you see, and oftentimes, this does not always work, but if you have some special gamma, maybe it's Z, maybe finitely generated, oftentimes finite groups, then you can lift properties from R0 to R. Okay, you see theorems of this kind. For example, R0 is Noetherian, then R is greater.
What is Q?
Say it again. P. Oh, just some property. I'm just talking in general. So if R0 has some these are the type of theorems you see in the literature. If R0 has some property, maybe Noetherian or like that, something, then maybe you would be able to lift it up. So that's one thing that still you can prove stuff. The other is that, so stating some sort of theorem. The other is that if R has property P, how is it? So if R has property P, then R has property GRP. So you'll see in a second what I mean by here. So you have a ring. You have properties for a ring. Okay? Noetherian, Artinian, semi-simple, and so on. You can define similar things in the setting of graded. So graded simple, graded semi-simple, graded Noetherian. And sometimes you can relate these, that if R has property P, then R has property graded P, or vice versa. An example, check this, I might be wrong here, but just check this. If R is Z graded, and it is graded Noetherian, I'll mention what this means, then R is Noetherian. Okay, so very quickly, so what is R being Noetherian? The concept is that if you have a ring and you have a chain of ideals which grows, it has to stop somewhere. So Noetherian means if you have a chain of ideals, it's not going to keep growing. It has to stop somewhere. At some stage you have AK, and it's not going to grow anymore. It's all going to be the same. So it's some kind of finite condition you put on a ring, right? So it's not going to grow. Now, what is it? So these are ideals. You'll see I'll define graded ideals. So if you have ideals, you have the notion of graded ideals. Now, graded Noetherian means these graded ideals stops. So this is ideals The same thing with graded ideals. Stops. Okay, now I'll define what is a graded ideal. These are ideals that you can also break it into pieces, right? So these are ideals with extra property. Now see what happened here. I'm saying that if on these level, on the level of graded ideals, the chain stops, it guarantees that chain always stops. So these are particular ideals. So I put assumptions on particular ideals, and I said there the chain stops. Then somehow you can prove that for any chain of ideals it stops. So this is another, I really like it. I think it's correct, but check it out. That you can lift properties or relate properties from the non-graded version to graded version or vice versa. And just a segue here. So remember this Leavitt path algebras. These are Z-graded. We get to this later. But just know that these are Z-graded. So you can write this LPI as this. Great. Now, you also probably heard that these algebras have very, very nice properties. Still people proving theorems about it. One reason I think that this works is that if you look at the LE0, so the zero component of LE, this is a very, very nice ring. It's ultra matricial algebra. So it means it's matrices, but it's a union of matrices. So these have very, very nice properties, and somehow you can lift the properties to LE. So that's why the Leavitt path algebras are nice rings. One reason is that what's sitting below them is a very nice algebra. So we get to this later. All right, now let me give you a couple of examples that you know these rings, but maybe you didn't know they are graded. So that means if I give you a ring, these partitions sometimes are not very trivial. You cannot see it right away. You might be able to partition rings, but it's not clear. So here it is. So imagine R is a ring. And look at the matrix ring. This is a graded ring. This is a graded ring. In fact, I think there are many different ways to partition this. Okay? But I'm going to give you the very nice ones. So Mn of R is a ring. It's a Z-graded ring. So I have to give you these components, right? So here it is. Let me call this A. So what is A0? The component assigned to 0 is this one. So I have to give you matrices which are coming from Mn of R. So put here all R, everywhere else 0. So this is a subset of this. Everywhere is 0 except on diagonal, you just pick up elements from R. Okay, that's A0. Remember that A0 is a ring, is a subring, and you can immediately see that this is the case here. You can add and you can multiply, you're always here, right? So this is A0. Now I have to give you A1, A2, A3, and so on. So first of all, I give you A negative. This is the arrangement I make. Below the diagonal, put R. Everywhere else, put 0. So just below the diagonal is R. Everywhere else is 0. Now, this is the example that you see. Well, this is a subset here, but this is not a ring. When you multiply A inverse with A inverse, you are not end up here. Yeah. So this is not a ring. It's just some subset of that. Now I have to give you A negative 2. And here is a negative 2. 0 on diagonal, 0 below diagonal, and just put here R. And everywhere else 0. And I think you got the idea how I'm going further. So this is a negative 2, and then I think it has to, let me just make sure I don't mess the indices. So this would be, I just go down the diagonal, put R there, 0, 0, everywhere else 0, the last bit here, R. And then, okay, so these are the components. And then flip this, so rotate this. So the transpose of this would be A1. I think this is the transpose. All the way. So now you can check that if you multiply 2 of these, you're in the next one. You can check this. And this is an example that you asked. The support here is just, what is the support? It's from here. So it's just a subset. So I like this because, I mean, if you look at this Mn of R in itself, it doesn't look like a graded ring, but if you do this partitioning, then it's graded. And as I said, this is just one way to partition this. There are all kind of ways that, you can put R in, just rearrange it in different ways, but in a smart way that this would be satisfying. Maybe I give you one more example. So this time, it's a finite group as the grading. So example, this is called the, let me see the name, formal matrix ring. So pick up 2 rings and 2 bimodules. So M is an RS bimodule and N is an SR bimodule. So the way you can think of this is that this is a set, it's an abelian group, that R and S are acting from left and right, and the same for N. Okay, so these are the data you have. Out of this, I'm going to construct a ring. Very simple when I put it here, but very difficult to study. The structure becomes complicated. So now, here is the set. Put the elements R and S here. R and S, just arrange it here. And M and N here. And then multiply, as usual. Okay. When you are adding, well, you are adding component-wise, that's fine because you are adding inside R, you are adding inside S, you are adding inside M and N. M and N are abelian groups, so that's good. But when you multiply, let's multiply 2. So let's multiply these. So I get R1, R2, that's fine. That's happening inside R. And then I get R1, R2, N1, N2. I just put it here because this doesn't have a meaning. M and N are just two separate entities. This is okay, so I'm multiplying this row with this column. This makes sense because R acts on M, so this makes sense. And S also acts on M, so this also makes sense. And see left and right, everything works fine. Let's do the other one. This should be also okay. N1, R2. N, R acts on N, so that is defined. S acts on N from left. This is also defined. This is not defined. I don't have. So in order to things tick here, so I define a map. Define these two maps also, and well, now when I write M1, M2, you understand that I'm just pushing elements here in here, and that goes to R, and this is in R, so it works fine. The other also, so two maps from this tensor product here, and remember this has to be associative, so that forces that I put one condition between these two, that M, N. So I have it here. M prime should be M prime. I think that's it. So you understand what I'm doing here. M times N, I'm just using this, I come to R, and then I multiply with M prime, this is defined. This is the same as, I do N and M here, I get to S, and then multiply with M, and I force this to be the same. Do I need the other one? I don't see from this I can get this one. I think I need both conditions.
Both conditions. Both are equal.
Yeah, both. I force both to be equal.
Both are equal.
So I put this because when you have three of these, the associativity should work. So that forces these two conditions. I put it here. I don't remember I have this in. So N times M gives you S, and S acts from left to N, that makes sense, and then M and N is R, and R acts on M from right. That's also good. And I don't see from here, from this one condition, I would get this. Okay. All right, so now, this is your ring. Now, with all this, it works. This becomes a ring. Now, it's a graded ring, so I have to tell you how I'm going to grade this. Okay, so here is one way to grade this. T0 is R00S. This is a ring. If you multiply two elements, still there. Okay, and T1, I put the other bit, because if I add them, I have to get the whole T. So I put 0 and Cn. So of course, T is the sum of this in a unique way, and this is a Z2 graded ring. I.e., you have to check that T1 times T1, you are end up here. But you would, because I have these maps. Let me show
you. If R and S are multi-equivalent, then
right. Yes. So that reminds you of that. So if R and S are Morita equivalent, then there are P and Q with
They'll satisfy
these
this
two
much.
maps. So if R and S are Morita equivalent, you always have a Morita ring. This is called Morita ring.
Can we
To make this
replace,
very simple,
can we replace gamma with any other category?
say it again.
Can we replace gamma, the gamma?
So here is Z2.
Right.
Well, I mean,
In general.
The group.
you have to give me the partition. I mean, if it's Z, you have to partition this into Z pieces. At the moment, I don't see how to make it Z. I mean, I can see very naturally into two pieces, and this is working.
There is a notion of group-wide credit rings also.
No, his question is that whether this grading can be defined by other structures.
Yeah, of course.
Semi-group grading,
Yeah.
group-wide credit.
For example, I take a category and I want to keep that partial multiplication of
Yeah,
the
I mean,
category.
okay, category graded.
Yeah,
yeah.
category.
I'll get to that. Yes, you can. Of course, you can. So, yeah. So R is a gamma graded. This is, I said, abelian group.
Right.
You can generalize this. I would write it down. Yeah.
So increasing the order of this matrix, we can get Z by NZ graded.
This one, yeah, I think you can, but then you have to be very careful here. I and J, J and R, and so you have a lot of these, and then you have a lot of maps. I would imagine you can.
So when we are considering the category graded rings, do we consider the ring as a single object pre-identity category, or we don't look at the ring as a category?
Well, I mean, okay, let me just write, okay, generalization. So R is a gamma graded ring. Okay. Now at the moment I'm working with gamma being an abelian group. Then I put the assumption R alpha, R beta is inside R alpha plus beta. Okay. You can generalize this. I'm just writing this so that I get to your question. You can just put group. Same story. R alpha, R beta is R alpha beta. But you can also put here semi-group because all you need is one thing. So it's putting semi-group. Right. So then R alpha, R beta is in R alpha beta as an example. Then this polynomial ring is an n-graded ring because I'm allowed to work with semi-groups, right? So that's semi-group. Now let's more generalize more. I put here a groupoid. So what is this? This is a category which all morphisms are inverted. Very, very limited. So any morphism you get, you can reverse it. This is called a group. You can put it here, okay? So then R alpha, R beta is, as usual, alpha, beta. This, if you can compose them in category, you cannot always compose the maps. If you can compose, you get this. If alpha and beta compose them. Otherwise, you just put zero. And then, of course, instead of gamma groupoid, you put category. The same story. That's what. But look, the thing is that you can do all of this. But I'm going to write theorems which works in this level, and it's not works in other levels. You cannot just, it becomes very general, then you cannot write theorems. Now that I'm here, for example, the best is that I've seen you can generalize theorems that you write for abelian groups. So there are papers on this level, groupoid, because oftentimes really you want to have an inverse. Like you have inverses here. So you want to have inverse. Therefore you work with groupoids. So for group weight grading, you have papers and you can prove theorems. The other that a lot of theorems goes through is for monoids, so like semigroups. Monoids, that means semigroups really. With zero, that can I write monoid? Monoid, that means you have an addition and you have a zero element. And I want this to be cumulative for abelian monoid. Okay, again like n. And again, as I said, you can just pick here monoid and everything works. But you cannot prove, I mean, it's too big to prove it. But if you put here cancellative, i.e., in your monoid you have this assumption, then a lot of theorems that you prove on the level of cumulative abelian groups goes through. You don't have inverses, but you have cancellative. So this is in terms of research in this direction.
Also, if there is two graded rings graded by two abelian groups, can we naturally extend it to the break sum or tensor?
Okay, then. So R is gamma graded and graded, two different grading. So how do you do that now?
I kind of meant that R is gamma graded and S is this omega graded. So is there any operation of rings that extends?
Yeah. That's. I mean, you just do R times this. Gamma times. Yeah. That's okay. But this one, so you partition R in two different ways, and you want to somehow combine them. If they are very different, I'm not sure at the moment. I mean, I'm gonna write now different way of partitioning. I mean, you start from here and you partition it in different ways. I'm gonna write in a second. But you're doing with two different partitioning. I'm not sure. I was thinking about like this. What are the chances this and that could do?
And given any group, abelian group, can we get a graded ring which is graded by non-trivial? Every component is non-trivial.
Yeah, I mean that would be a group ring. So for any group, you have group ring. That's a group ring. So now, yeah, grading is all about partitioning. So I'll just write the message here. Grading is all about partitioning. And rearranging. So let me just focus on the partitioning here. So imagine you have a ring R. Is gamma graded. And you have a homomorphism, group homomorphism. Then I can make R a omega graded. How am I supposed to do that? So R is, and eventually I want to write that now. This is gamma graded. I want to write it this way. So you have to give me now these components. So this is one way to do it. So you have to give me this these components, and these are tagged by omega, right? These are tagged by omega. And all I have is this one. So this is omega. What if I say anything goes to omega, I pick up those components, right? So alpha 1, alpha 2, alpha 3, they are all going to omega. I'm going to pick these, and I just put it here. And I have to be careful. In fact, something goes to omega. So this is if this is not empty. Otherwise, zero. Then you need to check, but it shouldn't be very difficult because this is a homomorphism that this is inside. So again, maybe the picture would be nicer. So imagine R, I partition this R. This is R. It's a gamma partition. And I know that gamma goes to omega. So all the elements which end up in one element here. So imagine R alpha, beta, and these are all end up in omega. So I call this R omega. This is my R omega. So as you see, it's coarser, right? This is, if that's correct way to say it, it's a coarser grade. Because it makes things just bigger, so you are kind of losing information. Okay, a couple of more of these things. So this was when you have a homomorphism, then you can make a gamma graded into omega graded. The other one is that, so imagine now this is just a sub, maybe this one. This is a subgroup of omega. Subgroup. And I'm still working with the abelian groups, so these are all normal, everything. Then I can say that R, then I'm constructing a new here. Maybe I'll call it this one. This is so how can I do this? So R has these components coming from omega gamma. I just pick up these components and put them next to each other. That gives me a subring. This is a subring of this. So imagine if R is Z graded. So then I have R0, R1, R2, and so on. And then I get a subgroup here, maybe 2Z, or maybe 3Z. I cannot get all of R. I'm going to get those pieces which appears in 3Z. So I just pick up R0, R3, R6, and so on. So these are my new grade. So that's another way to just pick the ones that we want to concentrate on. And then, can you give me one example of this? So I want to get one example of this. So can we do this together? So imagine you have gamma and you go to gamma over this. So this is a group of morphism. Now can you write this down? So R is gamma graded. And with this technique, R becomes now omega graded, omega being this. Now you have to give me these components. So R is a direct sum of R So I look at this, it fits in here. So now R is a gamma over. So this is this how do you call it? Yeah, this quotient. Yeah, what do you call this element? Yeah, gamma. So lambda. So gamma over lambda graded. And now this is just a formality that R is a direct sum of these. These are elements coming from here, but you have to now describe this formula. You have to describe this. Based on this here. So I have to tell you what are these. Well, these are all the elements in here. So I pick up all of these and then put it here. Now I get a coarser grading. So this grading is finer. So I can start with the Z grading, so let me give you an example, and make it coarser. In this example here, so R is a Z graded. Now, with this technique here, R is also a Z, 2Z graded. Right, Z2 graded, Z over 2Z graded, but I have to give you the components. And the components becomes
I have a confusion here. So when you consider this R is Z graded and R is 3Z graded, here in this
here.
yes, then this notations what you are writing as if you are taking R0, R3 from there, then that will no longer be a partition. So the notations are different.
So maybe this is not a good notation, but you agree this is a ring now?
But these are not those R3s, R0s, etc. They are different.
Yeah, so it depends how you, okay, first of all, you agree this is a ring?
No, my point is not that. My point is about the notation.
Yeah.
That means these R3 is not the same as the R3 above.
It's the same one.
Same one?
Yeah.
How will it be a partition then?
It is not partitioning the R, it is partitioning R lambda.
No, I'm not
R
sure.
lambda is a subring of R. It's not
So,
the whole ring.
This I named this R3Z.
Oh, I see. Not R.
No, R3Z. Maybe this is not a nice notation.
Oh,
Maybe
then
RS.
it's okay. Then
Yeah.
it's okay. I'm thinking that it's your partition R.
No. This is kind of a sub-ring of it, not kind. It's a sub-ring of R.
But here the thing is different. That here you are.
It's a different
grading-
one. This is different. This is different.
No, different. But here you are grading
On the
with
whole
respect to
ring.
Gamma, yes, whole ring.
This is the whole ring.
Yes.
But this is just a sub-ring. And this is just an example of this one here. So maybe it's my mistake to mix this. So this is a sub-ring. And let me just give you an example of this one here. So you have a Z-graded ring. You write it here. You pick up 2Z, which is sub-ring. Now I want to get this grading here. So what does that mean? That means that I'm going to have just two components.
Yeah.
One is R, 2Z, and the other is R, 2Z plus 1. I have only two components. And this gives me all of these. So these are all of these. And the other one is here. So another partitioning. So the whole point is that, yeah, so you can just handle these partitions the way you want. And now you can check that if I multiply these two components, I'm still here. If I multiply this and this, I'm here. And so on. Now that I'm here, let me just give you one more of these that really convey the fact that it's all about looking at the ring and then partitioning the way you think it's, working in your application. Okay, example. So now this time A or R is a gamma times gamma graded ring. Okay. And I'm going to partition it differently. I'm going to say that for any gamma in gamma, define A prime or R prime this way. R is a gamma times gamma, so you have all these components. So this can be written as so you have all these components. Now I'm going to define new components based on this. I could write also to example. Then convince yourself that this R is really, so I'm going towards now to make R a gamma graded, from gamma times gamma graded to gamma graded. Gamma graded with this. And here is for, just to give you a picture of this, for gamma to be Z, this is how it looks. Imagine gamma is Z. So you have a Z times Z grade. That means in each component you have some R. So here is R00, here is R01, R02, and so on. Here is R10, 20. So you can write it this way. And so on. And then convince yourself that this one, so look, let's go back again. R is Z times Z graded, so these are all the components everywhere. Now I want to get a Z grading, okay, with this definition. So I want to put all these components next to each other. So if you stare at this, you see that I'm putting all these components next to each other. I call it R0. I put all these components next to each other. I call it R1 and so on. And -1 And now, I mean, you can check it here, but that means if I multiply these two lines, I'm ending up in the next line.
Right.
Isn't this just the first case where you say from one group to another? From the first group here,
Yeah, I was thinking, I was thinking how to get that. So, is this an example of? So I go from gamma times gamma to gamma.
Yeah.
Maybe that's the one. That sits into this machine.